All right, problem 89 is all about describing on a molecular level why certain acids are stronger than other ones. So looking at A, nitric acid is a stronger acid than nitrous acid. So why is this? And the rationale behind this is the higher the oxidation state of the atom attached to the OH group, the more you're pulling electrons away from that OH group and weakening the bond, so the H pops off easier. So you have an oxidation state of +5 with the nitrogen and nitric acid as opposed to a +3 state in nitrous acid. So electrons get pulled away from the hydrogen-oxygen bond and make that H easier to take off. B, why is, there we go, stronger acid due to having a higher oxidation state. B, why is hydrosulfuric acid a stronger acid than water? Well, this is a different rationale here. We don't have an OH group. We have a hydrogen directly bonded to an atom. This has to do with bond length. The longer the bond length, the easier it is to break the H off of the acid. So sulfur is a way bigger atom than oxygen is. So as you go down a group, right, you get more and more shielding, bigger and bigger atoms, so easier and easier to break an H off that's attached to an atom. So it has to do with bond length. C, sulfuric acid is a stronger acid than hydrogen sulfate. All right, so when sulfuric acid gives up its H, right, that electron pair gets infused into the rest of the molecule and helps stabilizing it, making it harder to take subsequent H's off. So anytime you have a polyprotic acid, it's always easier to take the first H off. It gets harder and harder as more and more electrons get put into this molecule, helping to stabilize it. Where are we? Okay, so sulfuric acid is a stronger acid than selenic acid. I'm sorry. Yeah, sulfuric acid, selenic acid. So this isn't a question of oxidation state. Both of these atoms are oxidized the same. They have the same oxidation state. It's a question of electronegativity. Sulfur is more electronegative than selenide, so the electrons get pulled more away from the OH group, weakening the bond and making it a stronger acid. Same rationale with E. We have trichloroacetic acid versus acetic acid. The chlorines are more electronegative than the hydrogen, so electrons get drawn away from that hydrogen-oxygen bond in the OH group and weakening it, so the H pops off easier. So again, stronger acid due to the higher electronegativity of the chlorines. Identify the Lewis acid and Lewis base among the reactants in each of the following reactions. Right? So there's a raised definition of an acid, Bronsted acid-base chemistry, and then there's Lewis acid-base chemistry. Lewis acid-base chemistry, you look at it in a different way. The acid is an electron pair acceptor, and the base is an electron pair donor. So it's it's backwards from Bronsted, right? Proton, H plus donor as opposed to an H plus acceptor. This is an electron pair donor and an electron pair acceptor. So this isn't a redox reaction. Right? When we talk about forming this hydrate with iron 3, between iron 3 and water, perchlorate here is just the spectator. It's about water donating an electron pair and covalently bonding with the iron 3, right? So this is what you got here. All right, iron 3 is acting as an electron pair acceptor, and the oxygen's donating an electron pair to form a bond. So this is one big molecule, right? 6 waters bonded to a central iron 3. So I did a little little PowerPoint magic here. So here are the waters. There's the iron 3. The iron 3 is hungry for electrons. It doesn't have the power to take the electrons, so it's not a redox reaction. These electron pairs are donated and form covalent bonds, but there's no change in oxidation state with the atoms. So this is not a redox reaction. This is something different. This is a Lewis acid-base reaction. The waters are acting as electron pair donors. The iron 3 is acting as an electron pair acceptor. Cyanide ion complexing with water to form Oh, I'm sorry. Cyanide ion. Wait, I don't like these. We're used to this being a Bronsted acid-base reaction, right? And H being transferred from the water to the cyanide ion to make, the conjugate acid, hydrocyanic acid and hydroxide. Nonetheless, you can look at this in a Lewis acid-base sense. All right, so the cyanide ion is donating an electron pair to form a bond with the hydrogen. So it's technically acting as the Lewis base, and the water is technically acting as the electron pair acceptor. It's really the H plus ion. So water, there it is, right? So this electron pair gets donated to form a bond with the H. The electron pair gets let go between the hydrogen and the water to form hydroxide and cyanide ion. So looking at this, right, cyanide ion is acting as the electron pair donor. H is acting as the electron pair acceptor. So Lewis base, donor, electron pair donor, H, the electron pair acceptor, the acid. Like I said, don't like this one. Rather look at this in terms of Bronsted acid-base chemistry. H is being transferred. This one's more the classic case, right? So if I'm looking at this, the nitrogen has an electron pair to donate to the boron and boron trifluoride. So boron trifluoride is acting as the electron pair acceptor, the Lewis acid, and the nitrogen in this three methyl groups attached to, I forget what the name is, acts as the Lewis base. So that's what it looks like. Got that electron pair on this molecule being donated to form a bond with the boron. So hey, we've got sp2 hybridization with boron trifluoride, right? It breaks the octet rule because you can't bond more than once to fluorine. This electron pair gets donated. Instead of being 120, it now gets 109.5, right? So you change the hybridization by making this bond between the boron and the nitrogen. We used to call this coordinate covalent bonding. So coordinate covalent bonding is an example of Lewis acid-base chemistry. The electron pair being donated by the nitrogen, the electron pair being accepted by the boron. So both the electrons come from the nitrogen to make this bond. Right, so again, we're back to H is being transferred by what would you call that? Hypoiodic acid reacting with amide ion to form ammonia and hypoiodite. Again, this is a Bronsted acid-base reaction, but technically, I guess if the electron pair is being donated by the ammonia to bond with the H, it's acting like the Lewis base, and the H is acting like the Lewis acid. All right, problem 99, we dealt with this in an earlier problem, right? Predict which member of each of the pair produces a more acidic solution. And the answer to this is the more highly charged the cation, the more the electrons get pulled away when you form a hydrate. I mean, I don't think you form a hydrate with a +1 charge, right? So potassium ion doesn't do this with water, but the copper 2 does. So copper 2 is more highly charged, so it'll pull electrons more toward itself when it hydrates with water. Same with iron 3, same with, well, actually, when we talk about gallium and aluminum, then it's an electronegativity issue. So aluminum is more electronegative, so the electrons are going to get pulled more towards it when it hydrates with, forms a hydrate with water. So we looked at this earlier, smaller radius, all right, so more harder pull on the water molecules, weakening the OH group. So I said we did this earlier, right? So we've got a +2 charge on this hydrate, even more acidic if I put a +3 charge, or I manage to put a +4 charge on this. The higher the charge, the more it pulls electrons away from these OH groups, making it easier to pop that H off and lose it. So that's how it works. The more highly charged the cation, the more acidic the hydrate.